You've seen this picture 1,000 times, nucleus in the center. Electrons orbiting like planets. It's in every textbook, every classroom poster, every science documentary you've ever watched. But here's what nobody told you. That picture, it's not simplified. It's not close enough. It is fundamentally completely wrong. And we've known it's wrong for almost 100 years. In 1925, a 2-3-year old physicist named Werner Heisenberg was suffering from such severe hay fever that he fled to Helgoland, a tiny, barren island in the North Sea, with almost nothing on it. No trees, no pollen, just rocks and wind and ocean. And alone on that island, running a fever, barely able to see through swollen eyes, he didn't just find a better model of the atom. He destroyed the old one. He proved that electrons don't orbit anything, that they don't even have a position until you look at them. What he discovered that night was so disturbing, so fundamentally strange, that even the greatest minds of his generation, Einstein, Schrödinger, Bohr, spent decades arguing about what it meant. Some of them never accepted it. And yet, everything we've built since every laser, every transistor, every MRI, every smartphone you've ever held runs on the physics that came out of that tiny island. So in this video, we're going to do something your textbook never did. We're going to show you what's actually inside an atom, not the cartoon version, not the simplified version, the real version. The version that's so strange, so counterintuitive, that your brain will resist it. But by the end, you'll never look at the physical world the same way again. Let's start with what they got wrong. Take hydrogen, the simplest atom in the universe. One proton, one electron. That's it. So here's a question that sounds almost too basic to ask. Where is the electron? If you've seen the textbook picture, the little ball zipping around the nucleus in a neat circle, you already have an answer. It's right there, on the orbit, like a tiny planet going around a tiny sun. But here's the thing. The electron doesn't have a position. Not a fuzzy position. Not an approximately here position. It literally does not have a definite location until the moment you measure it. Let that land for a second. The most basic question you can ask about a thing, where is it, has no answer. Not because we lack instruments. Not because it's moving too fast. The answer doesn't exist until you force it to exist by looking. Before measurement, the electron exists in what physicists call superposition, a state where it could be found in many different places, each with a different probability. Map those probabilities in three-dimensional space, and you get something that looks like a cloud. Dense near the nucleus, fading at the edges. That's the famous probability cloud. But be careful. Because here comes the second mistake almost everyone makes. A lot of people hear probability cloud and picture the electrons smeared out like butter across toast. Spread thin. A little bit everywhere. That's not what's happening. The cloud doesn't show where the electron is. It shows where you might find it if you looked. And there's a massive difference. In an Einstein orbital of hydrogen, there's about a 90% chance of finding the electron within 5 angstroms of the nucleus that's null, 14 nanometers. But until you measure, it isn't at any of those points. So what is the electron? Then, this is where it gets genuinely strange. In quantum mechanics, the electron is described by something called a wave function, a mathematical object that encodes every possible outcome of a measurement, weighted by probability. And here's the part that breaks people's brains. The wave function isn't a description of the electron. It is the electron. There's no tiny ball hiding behind the math. There's no real particle underneath the equation, waiting to be discovered. The wave function is the complete, full, final description of reality at the quantum level. The wave function is the electron. That's all there is. And if that makes you uncomfortable, good. It should. It means you're paying attention. Now, you might be thinking, okay, fine, the electron doesn't have a fixed position. But surely it still moves? Surely it still goes around the nucleus in some kind of path? No. And here's why. If an electron actually orbited the nucleus like a planet around the sun, it would be constantly accelerating. That's just circular motion. And any charged particle that accelerates radiates electromagnetic energy. It loses energy. Continuously. Run the math, and an orbiting electron would spiral inward and crash into the nucleus in approximately 10 to the power of negative 11 seconds. That's 100 billionth of a second. Every atom in the universe would have collapsed before you finished reading this sentence. Obviously, that hasn't happened. You're still here. The screen you're watching this on is still here. So classical orbits don't just fail to describe atoms. They predict that atoms cannot exist. Okay, what if the electron just sits still? What if it parks itself near the nucleus? Not moving, just resting there? Also wrong. This is where Heisenberg's uncertainty principle enters. It says you cannot simultaneously know both the position and the momentum of a particle with perfect precision. Pin down where the electron is within, say, 10 to the power of negative 10 meters, and its momentum becomes wildly uncertain. Wildly uncertain momentum means wildly uncertain kinetic energy. Enough energy to blow the atom apart. So it can't orbit. It can't sit still. It can't be in any definite place. What's left? Let me take you back to the summer of 1925. Picture a 2-3-year-old Werner Heisenberg, face swollen from hay fever, eyes nearly shut, arriving on Helgoland, a barren rock in the North Sea. No trees, no pollen, no distractions, just wind and waves and the most terrifying calculations of his life. He can't sleep. At 2 a.m., he walks to the cliffs, running numbers in his head. By dawn, he's done something no physicist has ever done before. He hasn't found a better orbit. He hasn't tweaked the old model. He's thrown the entire concept of electron trajectories away. What Heisenberg realized on that island, what kept him awake until sunrise, is that you shouldn't try to describe where an electron is or how it moves. You should only describe what you can actually observe, the light that comes out when an electron changes energy states. And this is the insight most people never hear. The electron doesn't orbit. It doesn't sit still. It doesn't travel from point A to point B. It just is. It exists as a wave function, not a thing in a place, not a particle on a path. A quantum object that exists in a fundamentally different way than anything you've ever held in your hands. And that realization, born on a tiny island in the North Sea, in the mind of a feverish 2-3-year-old who couldn't stop sneezing, is what makes everything we build in the rest of this video possible. So the electron exists as a wave function. Fine. But wave functions aren't random. They can't be just any shape. The wave function has to satisfy a set of rules, the Schrödinger equation, and only certain solutions are allowed. Certain shapes, certaines énergies, we call these shapes orbitals. And right here is where most people make the next mistake. An orbital is not an orbit. It's not a path. It's not a trajectory the electron follows from point A to point B. An orbital is a region of space, a probability map showing where you're likely to find the electron if you look. The simplest one, the ground state of hydrogen, is spherically symmetric, a fuzzy sphere. Probability highest near the nucleus, fading as you move outward. No orbit, no path. Just a cloud of might be here. But go higher in energy, and the shapes get strange. Some look like dumbbells. Two lobes of probability on either side of the nucleus, with a flat node in between where the probability drops to exactly zero. The electron will never be found at that plane. Ever. Not sometimes. Not rarely. Never. Go higher still, and you get donuts. Cloverleafs. Multi-lobe structures that look more like abstract sculpture than anything you'd call atomic. But remember, these aren't physical objects. They're probability distributions. Maps of where you might find something that doesn't have a definite location. Now here's what really breaks things. When an electron transitions from one orbital to another, say, from a higher energy state to the ground state, it doesn't slide. It doesn't gradually morph from one shape to the next. It doesn't travel through the space between the two orbitals. It jumps instantaneously. One moment, the wave function has the shape of the higher orbital. The next moment, the lower. No in between. No smooth transition. No mechanism anyone can describe. This is a quantum leap. It jumps instantaneously. How? We don't know. The math describes it. The experiments confirm it. But there is no mechanism. No explanation for how the electron gets from here to there without passing through the middle. It just does. And here's what makes that matter, outside of a physics lecture. Every laser you've ever seen works because of quantum leaps. Every LED in your room right now, the light from your phone screen, quantum leaps. Billions of them. Every second. The strangest thing about atoms isn't some abstract curiosity locked in a lab. It's lighting your room. Right now. So the electron exists as a wave function. It occupies orbitals. It makes quantum leaps. But what is it? Is it a particle? When you detect it, you always find a localized point. A dot on a screen. A click in a detector. Never a smeared out wave. Every single time, a particle. Is it a wave? When you're not looking, the wave function spreads, interferes with itself, diffracts around obstacles, all the things waves do. Every single time, a wave. So which is it? Neither. The electron is not a particle. It's not a wave. It's a quantum object, something that doesn't have a classical analogy. Something that shows particle-like behavior in some experiments and wave-like behavior in others, but is fundamentally neither. And that's not a limitation of our understanding. That's the answer. If this sounds abstract, let me make it concrete. In 1989, scientists at Hitachi did something extraordinary. They fired single electrons one at a time through two tiny slits in a barrier. One electron, then another, then another. Each electron hit the detector screen as a single dot. A particle. No ambiguity. But here's what happened when they let the dots accumulate. After hundreds of electrons, thousands, the dots formed a pattern. Not a random scatter. Not two stripes behind two slits. An interference pattern. Bright bands and dark bands. The signature of waves overlapping. Each electron traveling alone, one at a time, with no other electron to interact with, had somehow gone through both slits simultaneously and interfered with itself. Each electron had interfered with itself. Physicists named it the most beautiful experiment ever performed. Now here's where it gets truly disturbing. When you're not observing which slit the electron goes through interference pattern, waves. But the moment you set up a detector at the slits to watch which path the electron takes, the pattern vanishes. Two stripes. Partículas. The act of measurement doesn't just reveal what was already happening. It changes the outcome. The wave function that spread out, interfering, both slits at once mathematical object collapses. Instantly. Into a single, definite result. Here. Not there. And nobody knows how this happens. Not as a figure of speech. Not as dramatic exaggeration. Nobody knows what counts as a measurement. Nobody knows why observing the electron changes its behavior. Nobody knows where the wave function goes when it collapses. This is called the measurement problem. It has been haunting physics for almost a century. There are interpretations. Many worlds where every measurement splits the universe into branches. Pilot waves where hidden variables guide particles along definite paths. Objective collapse where wave functions break down spontaneously at certain scales. But they're interpretations, not answers. The math works. The predictions match experiments to astonishing precision. But what's actually happening when no one is looking? We don't have a clear picture. And if that bothers you, good. It bothers physicists too. Let's make it worse. Let's add more electrons. Hydrogen has one. Simple enough. One wave function, one probability cloud, one quantum mystery. But helium has 2 electrons. Lithium has 3. Carbon has 6. Iron has 26. Uranium has 92. And here's where something deeply strange happens. All of these electrons, every single one in the universe, are identical. Not similar. Not close enough. Absolutely. Perfectly. Fundamentally identical. There is no serial number. No scratch mark. No hidden property that distinguishes electron number 1 from electron number 2. They're not two different things that happen to have the same properties. They are the same thing appearing in 2 places. That sounds like philosophy. It's not. It has a measurable consequence that holds the entire physical world together. If you swap 2 electrons in a system, mathematically exchange their positions, the wave function of the entire system changes sign. It picks up a negative factor. And this one mathematical fact leads to a rule so powerful it explains almost everything you see around you. It's called the Pauli exclusion principle. No 2 electrons can occupy the same quantum state. Wolfgang Pauli was 24 when he figured this out. One rule. That's all it took to explain why the periodic table has the structure it does, why matter is solid, why chemistry works. One rule. Nobel Prize. Think about what that means. If one electron already occupies a certain orbital with a certain spin, no other electron can be in that exact same state. They have to stack up. Fill different orbitals. Build structure. Layer by layer. This is why the periodic table exists. This is why atoms aren't all the same. This is why some elements are metals and others are gases. This is why chemistry works. This is why molecules can form. This is why proteins can fold. This is why you exist. Without Pauli's rule, all electrons would collapse into the lowest energy state. Every atom in the universe would be chemically identical. No complexity. No molecules. No chemistry. No biology. No you. Look at your hand right now. That solid thing you see? It's solid because of Pauli's rule. Without it, your hand. So, this room, every star, all would collapse into identical blobs of nothing. But why? Why does swapping two identical particles flip the sign of the wave function? Why this rule and not some other? We don't know. It's one of those facts about the universe that we discovered, confirmed, built an entire civilization on top of, and still cannot explain. It just is. And everything depends on it. Now, let's talk about the nucleus. Because you probably think that part, at least, is simple. A bunch of protons and neutrons packed together. Little balls stuck to each other. Wrong. Again, protons and neutrons are not fundamental particles. They're not the bottom of the ladder. They're made of smaller things, quarks. 3 quarks each. Up quarks, down quarks, held together by the strong nuclear force, which is carried by particles called gluons. But even that description is misleading. The quarks inside a proton don't sit still. They're quantum fields fluctuating, interacting, constantly exchanging gluons. The inside of a proton is one of the most violent, chaotic environments in nature. The proton doesn't contain 3 quarks the way a bag contains marbles. The proton is a bound state of the quark field, a stable pattern of oscillation. Not objects inside a container, a pattern that the container and the objects are made of. And here's where it gets truly strange. You'd think the mass of a proton comes from its quarks. 3 quarks add up their masses, get the proton mass. Simple. Except the quarks account for less than 2% of the proton's mass. Less than 2%. The other 98%? Energy. The kinetic energy of quarks moving at near light speed. The energy stored in the gluon field binding them together. Math C 44. Mass is energy. The proton's mass is almost entirely made of binding energy, not stuff. What's inside a proton? Energy. Bound field energy. Not stuff. Not particles. Energy arranged in a stable pattern. And the protons and neutrons in the nucleus, they're held together by the residual strong force, mediated by particles called pions, which are also made of quarks, which are also quantum fields. It's quantum fields all the way down. In 2012, the Large Hadron Collider at CERN, a machine 27 kilometers in circumference, buried 100 meters underground, built by over 10,000 scientists from 100 countries, confirmed the last piece of quantum field theory, the Higgs boson, the mechanism that gives particles their mass. $13 billion, all to confirm what the math predicted. So the nucleus isn't a cluster of solid balls. It's a roiling storm of quantum fields. And those fields, the quark field, the gluon field, they don't stop at the edge of the proton. They fill all of space. Everywhere. Always. Which brings us to the biggest question of all. So what is inside an atom? We've stripped away the orbits. We've dissolved the little balls. We've shown that the nucleus isn't a cluster of solid objects, but a roiling storm of energy. That mass itself is almost entirely binding energy, not stuff. So what's left? What is actually, fundamentally, at the bottom of everything? Not particles, not little balls, not orbits, not stuff. What's inside an atom is fields, quantum fields. The electron isn't a tiny dot somewhere in the cloud. The electron is a vibration in the electron field, a field that fills all of space, everywhere, at all times. When we say there's an electron here, what we mean is the electron field is excited at this point. A ripple, a localized disturbance. Same for quarks. The quarks inside a proton are excitations of the quark field. The gluons holding them together, excitations of the gluon field. The photons carrying electromagnetic force excitations of the electromagnetic field. Every particle you've ever heard of is not a thing. It's a pattern, a specific vibration in a specific field. The atom is not a thing. It's a pattern, not a tiny solar system, not a bag of parts. A temporary, stable pattern of excitation across multiple quantum fields, interacting according to precise mathematical rules. The atom is not a thing. It's a pattern, and so are you. You don't like this. I know. Your brain is built to think in terms of objects solid, definite, located somewhere. But at the deepest level of reality, there are no objects. There are no solid things. There are no little balls bouncing around inside atoms. There's just math. Fields described by equations. Patterns that emerge, persist, interact, and dissolve. There are no solid objects at the bottom. There's just math. Your body, every atom in it, is a pattern in quantum fields. The carbon in your bones, the oxygen in your blood, the iron in your hemoglobin, all of it is quantum fields, vibrating in stable configurations. You are not made of stuff. You are made of patterns in stuff. And even the stuff is just more patterns. Touch the table in front of you. Go ahead. Press your fingers against it. You've never touched anything in your life. What you feel is electromagnetic fields pushing against electromagnetic fields. Two patterns of excitation, refusing to overlap. Tell someone that tonight. Watch their face. And if that disturbs you, if the idea that solid objects don't really exist at the quantum level makes you uncomfortable, then you're paying attention. Because that discomfort is the feeling of understanding something true. Now that you know what an atom really is, a pattern in quantum fields, let's talk about the properties of that pattern. Because they make absolutely no sense. Start with size. You've heard the analogy. If an atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line. The rest? Empty space. But even that is misleading, because the space isn't empty. The vacuum, what we used to call empty space, is seething with activity. Virtual particles flickering in and out of existence. Quantum fields fluctuating at every point. The vacuum has energy. It has structure. It pushes back. The nucleus is about 100,000 times smaller than the atom that's real. At the scale of 10 to the power of negative 15 meters versus 10 to the power of negative 10 meters. But calling the rest empty is like calling the ocean empty because you can't see the currents. Now, the electron. How big is it? As far as every experiment has ever been able to determine, it has no size. 0. Point-like. We've probed it down to scales of 10 to the power of negative 18 meters. No structure. No surface. No edge. A thing that has mass, has charge, or has angular momentum but no physical size. No volume. No surface area. Nature doesn't care whether it makes sense to you. And then there's spin. Every electron has a property called spin. It's called angular momentum. And your brain immediately pictures something rotating like a top, like a planet. But the electron isn't spinning. It has no size, nothing to spin. And yet it has angular momentum. Measurable. Precise. Always the same value, spin 1/2. Spin 1/2 means something genuinely bizarre. If you could somehow rotate an electron by 360 degrees, a full turn, it wouldn't come back to its original state. You'd have to rotate it 720 degrees, 2 full turns, to get back to where you started. Nothing in everyday experience does this. Nothing you've ever held in your hands behaves this way. And yet every electron in the universe does. Every single one. And if you think this is just abstract physics with no real-world consequence, that MRI machine at the hospital, it works by manipulating the spin of hydrogen nuclei in your body. Spin the property that can't be spinning. So atoms have no solid parts. The empty space isn't empty. The electron has no size. And it has angular momentum without rotating. These aren't edge cases. These aren't unsolved mysteries. These are the confirmed, measured, repeatedly verified properties of the things that make up everything you see. Reality, at the quantum level, is not required to make sense to you. It's only required to be consistent with experiment. And it is. Ruthlessly. And here's one more thing that doesn't make sense. Energy inside an atom comes in fixed amounts. Not any amount you like. Specific, discrete amounts. Like steps on a staircase, you can stand on the first step or the second step. But you cannot stand between them. Think of a guitar string. Pluck it, it vibrates. But it can only vibrate at certain frequencies. The fundamental, the first harmonic, the second harmonic, specific patterns. Nothing in between. The electron's wave function works the same way. It has to fit around the nucleus like a standing wave wrapping around a sphere. Only certain wavelengths fit. Only certain energies are allowed. Everything else is forbidden. When an electron drops from a higher energy level to a lower one, it emits a photon, a particle of light, with exactly the energy difference between those two levels. Not approximately. Exactly. Hydrogen's signature, a specific red line, a specific blue-green line, a specific violet line. Each line corresponds to one particular jump between energy levels. It's a fingerprint. Every element has its own. And we can read those fingerprints from stars billions of light years away. Now, how precise is this theory? In the 1940s, physicists developed quantum electrodynamics, QED, the mathematical framework describing how light and matter interact. Richard Feynman was one of its architects. QED predicts the anomalous magnetic moment of the electron to 12 decimal places. Experiments at NIST and Harvard match. 12 decimal places. That is the most precise prediction in all of science. Nothing else in human knowledge comes close. Not engineering. Not medicine. Not any other branch of physics. 12 digits of perfect agreement between theory and experiment. But why are energy levels quantized? Why steps and not a ramp? The math tells us. The experiments confirm it. But there is no deeper reason. It simply is. So quantum mechanics works with terrifying precision. But there's one more thing you need to see. And this one is the hardest to accept. To look inside an atom, you need light with a wavelength smaller than the atom itself. Visible light won't work. Its wavelength is thousands of times too large. You need something with much shorter wavelength. End quote. End quote. End quote. Which means much higher energy. Here's the problem. The moment you use a high-energy probe to look at an electron, you slam into it. You knock it out of its state. You change what you were trying to measure. This is not a technology problem. It's not that our instruments aren't good enough. It's not that we need to be more careful. It's fundamental, written into the structure of reality itself. To see something small, you need short wavelength light. Short wavelength means high energy. High energy means massive disturbance. There is no way around it. There is no clever trick. The act of observation changes the thing being observed. And here's where it gets truly strange. Before you measure, the electron exists as a wave function, a superposition of possibilities. It's here and there. It has this energy and that energy. Multiple states simultaneously. The moment you measure collapse. One state. One position. One answer. Definite. Final. But the measurement didn't reveal a pre-existing reality. It didn't uncover something that was already true. It created a definite reality from a fuzzy one. The measurement doesn't reveal reality. It creates reality. Before you looked, the electron had no definite position. Not because you didn't know where it was, because it genuinely didn't have one. The question, where is the electron, had no answer until the moment you asked it. This is not interpretation. This is what the math says. This is what the experiments show. And no one, not a single physicist on Earth, can tell you how or why this happens. The universe, at its most fundamental level, does not decide until it is forced to. So let's bring this together. You came into this video with a picture, a nucleus in the center, electrons orbiting like planets. Clean. Simple. Wrong. What's actually inside an atom is nothing like that picture. Electrons don't orbit. They don't have positions. They exist as wave functions, probability clouds that collapse into definite outcomes only when forced. The nucleus isn't a cluster of solid balls. It's a storm of quantum fields, and 98% of its mass is pure energy. Every particle you've ever heard of is not a thing. It's a ripple in a field. Not stuff. Math. Patterns described by equations. And those patterns, verified to 12 decimal places, are the most precisely confirmed predictions in the history of science. Richard Feynman understood this better than almost anyone. He helped build QED, the theory that predicted the electron's behavior with a precision nothing else in human knowledge has ever matched. And when asked what atoms are really made of, he didn't point to particles. He pointed to equations. Feynman once said that if all of scientific knowledge were to be destroyed, and only one sentence could be passed to the next generation, it should be this, that all things are made of atoms. But what we've shown you today is what Feynman knew that sentence really means, not tiny balls, not solar systems, not stuff at all. Patterns in quantum fields. Math made real. And that not the cartoon, not the textbook picture, that is what you're made of. Not comfort, not simplicity. Truth. Now everything I've told you today is sourced. The experiments, the numbers, the history. Links are in the description. If I got something wrong, tell me. Leave a comment. I will correct it. That's not weakness. That's how science works. That's how this channel works. And if this video changed how you see the physical world, if you now understand what's really inside an atom, not just the cartoon version, do something for me. Ask someone tonight. A friend. A coworker. A family member. Ask them, what's inside an atom? And when they say electrons orbiting a nucleus, watch their face when you tell them the truth. Because physics isn't about memorizing models. It's about understanding reality. And you just did. Next time on Feynman Physics, we're going even deeper. Because the quantum fields that make up atoms don't just sit there. They interact. They exchange particles. They create forces. And the rules governing those interactions are so elegant, so precise, that they might be the most beautiful thing humans have ever discovered.